of A-level maths, and that is to have a look at trigonometric ratios. Most people are okay with simple trig of doing right angled triangles, but it's when you move on to the sine rules, the cosine rules, and then try and do trig of any particular angle, really does cause some problems in understanding how they work. So we'll dive in and we'll have a look and see what we can do here. What I'm going to start off with is, that's better, I can zoom in, looking at what rules that we've got to try and help us. We have various things. We have the cosine rule. The cosine rule is designed to help us find either a missing side or a missing angle. And this is not particularly sort of obvious when I get students trying to play with this. So let's have a triangle. And in this triangle, what we want to do is we want to work out a missing side. To have a missing side, what we need is two sides plus an angle. So let's just put these in here. Let's have B, we've got C, and we need this angle. And when we have this angle is basically opposite the missing side. And as long as it's like that, we can actually use this to work out what we're trying to find. And we've got two formulas to help us. We've got a squared equals b squared plus c squared minus 2bc times the cos of my angle theta there, which we normally write as cos A. So this side is our side A. And we can easily then work these things out. I'm not going to do one of these. It's reasonably simple. Most people met this at GCSE. If you want to try and do the formula to find the missing, this time, angle, then what we need to have is three sides. And then we can rearrange that formula to say that cos of A equals b squared plus c squared minus a squared all over 2bc. If we think about some of these, this first formula, if I take that bit off, is really the same as Pythagoras. So it's not too difficult to try and do some of these little problems. And as I said, most students have met these at GCSE. If we look at the other rule, the sine rule, this is basically, there are two versions of this, and again the two versions are to find a side or to find an angle. If we're going to try and find a side, let's just take again some sort of triangle. We're going to call this angle A, so this is going to be side A. If this is angle B, then this is going to be side B, and if this is angle C, this is going to be side C. Now, the sine rule then is A divided by the sine of A equals B divided by the sine of B. Similarly, I suppose we've got C is the sine of C. The side is equal to, if you like, a ratio, a proportion of the angle. The wider the angle, the larger the side's going to be. So if I take just the first part of this, we've got A over sine A equals B over sine B, and if I want to find angle A, for instance, side A, then side A is going to equal B times the sine of A over the sine of B. If I want to do the sine rule using this to find an angle, then it's easier if we take this ratio and turn it upside down. And so what we can do is we can say for this triangle that the sine of A over A equals the sine of B over B. And to work out the sine of A, this is going to be the sine of B divided by B times the sine of A. And this gives us a series of different ways of solving some different problems. And we look at typically a triangle, and you can try and work out various things. Normally, if we've got a triangle to solve like this, and I'm trying to work out a particular angle, then I'll have A and I'll have this one, and then I will have my B, and then we need to find that particular angle. And so this is the type of format we'll see in a particular sum to try and do this. So these we've met at GCSE, and the final bit that goes with this is to try and find the area of the triangle. And almost from junior school you'll have learnt that the area of a triangle is going to equal a half the base times the height. And that is simply because if we take any rectangle, turn it into a triangle, it's going to be half the area of this rectangle, which is going to be our base times our height. If we're going to work out this with trig, then we've got a non-right angle triangle to play with, and so we need two sides, and let's just put in here two sides. So let's have here side A, side B, this will be side C, and we will need to have the angle of C. So this gives us a very similar formula, which is going to be a half of AB times the sine of this angle. And the larger this angle, basically the larger, the higher this line is going to be. So it's going to be sort of a proportion of this. So these aren't particularly difficult, but understanding where they come from causes an awful lot of problem. And this is where I want to try and concentrate most of my time today, because these things aren't particularly easy. So we're going to try and look at where these things come from. And to do that, let's go back to some real basics and see if we can understand how it all works and where we get everything from. So let's go back and have a look at our standard trig ratios. We learn that if we've got a triangle that we've got here, and it's going to be a right angle triangle because we're going to be trying to play with some trig, that if this is going to be our angle we want to find, and we'll call it x for argument's sake, then this side we label as the hypotenuse. This side is as far away we can get from the angle x, it is opposite, and this side here is next to the angle and is adjacent. And we have our thing that we remember, SOHCAHTOA, and SOHCAHTOA here we know that the sine of our angle x is going to equal the opposite over the hypotenuse. We know that the cosine of our angle is going to equal the adjacent over the hypotenuse, and our tangent of our angle is going to equal the opposite over the adjacent. And this is all standard GCSE maths, and hopefully everyone's really happy with this. And this is all to do with right angle triangles. But let's suppose we don't have a right angle triangle. What are we going to try to do with this? And here we come to a rather nasty little diagram which students loathe. So let's try and draw out I did argue with myself whether I should bring a compass to try and draw this, and I thought, well, it'd be quicker without, but it's probably best if I should have, but we'll do as best we can. Now let's have a look at a particular angle and see what we can do with this angle. So let's suppose that this is a circle of radius 1. So if this point is 0, this point will be 1, this will be 1, this will be -1, and this will be -1, and in fact -1, -1 if we want to look at it. So I've just drawn in a simple circle, and if I look at an angle, and let's give this angle a name, we'll call it X here, then I can work out this as a right angle triangle, because what I need to do is drop a perpendicular down from there, and what I've got is simply a right angle triangle. We've got this distance here, which we know is going to be less than 1, and we've got this distance here, which we know is going to be less than 1. And we could just read this off along there, which is what you do when you're trying to work out one of these things. Right, so all the angles here are positive. But what happens if I now take an angle which is over this side, and the angle here is much larger? Well, what we can still do is drop a perpendicular, and I can still read across here what the height of my triangle is. So if we look at, for instance, the sine of something, then if my angle is from here up to 90 degrees, then we'd expect this to be okay, this is going to be positive. If I continue this angle and make this angle now an obtuse angle, then if I read this number here, it's still going to be a positive number. It will be, of course, negative here, but let's see what we need to know for sine. Sine is going to be the opposite over the hypotenuse. Well, this is the hypotenuse, and if I've set this distance to be 1, then this distance is going to be 1 all the time. So the hypotenuse is going to be 1. And if we look at my height here, which is, so we've got my hypotenuse. If we look at the opposite here, this is a number, and it's going to start off really low. It's going to go up and up and up and up, and then it's going to go down. It's still going to be positive. So all my values of sine from 0 right round to 180 are all going to be positive. What happens if we take this angle and move it round much further, making here a reflex angle? Well, here my value for my opposite is now going to become negative. And as it becomes negative, and this number is going to be positive, my values of sine are going to be negative. So we can think of that all my sines from 180 round to 360 are going to be negative. We can do exactly the same with cosine, and let's just quickly look at that. So if I'm going to look at cosine, we're going to try and draw one of these awful circles again. They don't get any better. If we're going to look this time at the cosine of my angle, we know this is the adjacent over the hypotenuse. So let's look at what we're trying to do here. If I'm looking for my angle x, we know my hypotenuse is always going to be the same length. It's going to be 1 because it's a radius. And this time we're looking at the adjacent. And when the cos is in the range from 0 to 90, then this adjacent value is going to be positive. If I now try and draw my cos over on this side, now my angle has increased to become an obtuse angle. Now my value of my adjacent here is going to be negative, and it's going to stay that way right round to 270. So I can think that my cos from 90 to 270 is going to be negative. But when we get round to 270 to the 360, any triangle in this area, I'm trying to work out where a good place to try and put it here, my adjacent value here is now going to be positive. So we can think of my cos somewhere between 270 and 360 degrees is going to be positive again. We can do exactly the same thing with tan. And for convenience, I will quickly do that of tan. This is really just so I can draw that awful circle again. And try as I may, they don't get any better. If we look at the tangent of a particular angle, so this is going to be angle x, we know that the tangent is going to equal the opposite over the adjacent. So if we look here, we've got my opposite, which is positive, and my adjacent, which is positive. So for a tangent, if we've got a number between 0 and 90 degrees, then it's going to be positive. If we draw this in as an obtuse angle, then this angle x here, my opposite value is still going to be positive, but my adjacent value down here is going to be negative. That's also going to be true if I move my triangle further round into this quadrant, and here we're going to find that the opposite is going to be negative, and my angle that is adjacent is also going to be negative. So let's just write this down. We've got the tangent here of 90 degrees to 180 degrees, and this is negative. And we're finding that when we get round here, the tangent of 180 degrees to 270 degrees, both numbers are negative. And if we've got both numbers negative, then our answer is going to be positive. And if we continue this circle right round here to our fourth quadrant, then we've got one of our triangle numbers. Our adjacent is now going to be positive, but our opposite is going to be negative. So the tangent between 270 and 360 is going to be negative. So we can draw out our cast diagram. If I draw out my circle, we know here that all of the sines, coses, tans are going to be positive. In this quadrant only, sine will be positive. In this one, only the tangent is positive, and in the last one, only cos is positive. And that gives us C-A-S-T, cast. Some remember it as the other way round, axe. And when I was a child, I learnt all silly tomcats. But as long as you remember the order, it doesn't matter. All is always in this particular quadrant. Now, that's one way of looking at it, but there is perhaps a different way of trying to have a look at this, and we'll see if we can work out what's going on. Now let's go back and do the sine again, and this time I want to look at it slightly differently, and sometimes I found this has helped my students understand how this works. The circles, as I said, do not improve. Let's draw in here for my sine. If I've got my sine, we've got the opposite over the hypotenuse. We know for the sine of this angle, this side is going to be 1 because we've got a unitary circle which aids the definitions of this, and this side here is my opposite. And I see what this is by simply looking at how it's moving up and down against this line. Now what I have got is a protractor that I prefer using to most, and instead of being a half protractor, this is a full protractor. And for working out things like bearings, it's really easy, but when it comes to trying to work out what we're doing here, it's often a lot easier to use as well. So let's have a look at trying to see what happens when we draw a sine curve with this protractor. So what I'm going to do is I'm going to draw out an axis. And let's set out a few things to try and draw this on. So let's look at what we've got for size, and if we say this point here is going to be 90 degrees, 180, 270 and 360. And what I'm going to do is I'm going to set up here this point to be 1, and I'm going to set up this point here to be -1. And I can set a couple of values here. We'll just make life a little bit easier. This is a half, and that's -1/2. So we've got 90 degrees, 180 degrees, 270 and 360. Now for this little bit, we're going to try and divide this up a little bit more to make life a little bit easier. And I'm going to try and take some different values here. So there is going to be my 45 degrees, and we'll see what we can do. I'm going to put my protractor on here, and we'll see what we can do with this. So if I set my angle here to be 30 degrees, then I'm going to have a hard time here, aren't I, trying to translate this. Didn't plan this as well as I wanted. We'll make a little adjustment. I'm going to make my ones a little bit further up. So let's just quickly change this. Right, so here is my position 1 at the edge of the protractor, -1, and if I take a quick measurement of this, that's 5 centimeters, so 2.5 will be half, and it's going to be the same here. That might be a little bit easier for me to work on. That should be a bit better. Right, so when I get this set to 30 degrees, if I can set my ruler across here, I'm running into big pen problems here, being in the way, then if I put my ruler down here, then when I'm at 30 degrees, we get a half. So this is going to be 30 degrees. So let's measure up 30 degrees. That's going to be about 1/3 of the way along here. So a third's going to be about there. We'll try 45, it might be a bit easier. So let's go for 45. So I'm up to 40, 45 there. And this is my height at this point. And I go along, and there is my little cross. Easier if I do 90, because at 90 it's going to be right up here at 1. So at 90 I've got 1. Of course, we also know it's going to be a value at 0. Let's just carry on looking here. If we're now going further round here on the angle, so I'm at 90 degrees, if we go to perhaps halfway between 90 and 180, then this is going to be our 45 degrees. So I can set my 45 degree mark, put my ruler in, and surprisingly it's at the same height as that point. If we were to try and do my point down here, it's probably going to correspond to my 30 degrees, which is going to now be all the way around on my blue to 150 degrees, and that's going to be a half. We'll go round to 180, it's going to be 0. So we're going to have another point there and 0. Let's carry on. I'm going to try just a few other ones. We're going to carry on round here to 45 degrees, going round more, and at that point we've got on my ruler so we're going to be about here. I didn't mark in my 45s. Doing this on a clever whiteboard is sometimes a little bit easier. And if we then move along to where we get to 270, we're back down to 0. Let's move along here. We're now 45 more degrees along here. So there's my height. At that point, about there, and at 360 we're back to 0 again. So I've got a few points to look at, and let's see if we can draw up these lines. I've done a few more at the beginning.
I'm reminding you, take up written tablets.
So let's try and draw this up. And what we get with my usual awful drawing is I've got the shape of a sine curve. We can do exactly the same thing with the cos, and I'm going to do this one quite quickly. So let's start off with, yeah, my ruler. Let's mark in -1, 0, half, +1, 1, half, 0, -1/2, -1. I normally get my students to do this, and it takes them quite a long time to try and get this really neat, but I'm doing it very quickly here with you, just so you've got an idea of how this works. Let's try and give myself a bit more space this time. 90, if I can, 90, 180, yeah, it'll just about fit. 270 and 360. Right, just about fit on the screen. We're looking at the ratio of cos, and the ratio of cos, we know, is the adjacent over the hypotenuse. So as we're looking at this diagram, then we know that when we're looking at this simple cos from our previous sort of cast diagram that we drew, that when we're in here, cos is going to be positive because we're looking at the hypotenuse and we're looking at the adjacent. But when it's over this side, our adjacent value will be negative. Let's have a look and see what happens. If we're looking at our adjacent over our hypotenuse, then we want to look at a slightly different relationship. When we're at 0 degrees, then what we're going to have for what I'm trying to measure here, so I want 0 degrees, and we're going to do it this way round, because if I look at what I've got here at the bottom, if I take this particular quadrant and let's expand it, and I draw a circle that's a triangle which is virtually up here, we're approaching the time when this hypotenuse, which is 1, and the adjacent will shrink down to be 0, because we've got our adjacent and our hypotenuse, and as it's doing that, we are approaching the value of 1. So our value here that we're trying to read is changing there. So we're going to have it at 1. So at 1 it's there. If we go across to 45 degrees, then I've got to try and choose where my point is. I didn't put them in, I failed. So here's my 45-degree lines. So let's put in here 45. This is 90, 180, 270, 360. So when I'm getting my 45-degree line, then at 45 degrees it's going to be about this point. When we get round to 90 degrees, we're going to be down here. As we move further round here, now this point here are 45. There's Philip not being able to read where the 45 was. There it is. So that's about there. Keep going around to 180 degrees, which is going to be down here. Our 270 is going to be there, there, and our 360 is going to be about there and up here. So if I draw this line in, this will hopefully make for a slightly better curve. So I've given an idea there about how we get cos working, and we can do exactly the same thing with tan if we want to try and work out what we've got. Now if we want to try and have a look at the tangent, then it produces a slightly different graph for us. So I'm going to set up this as before. And if I've got my 90, 180, 270, 360, and I'm going to put in my 45s as well. Let's label these 90, 180. There we go. And I can put my half and my 1 in. So minus a half, minus 1. There, we've got that one drawn in. Our tangent is, as we know, a different relationship. Our tangent is our opposite over our adjacent. So we know that, and so what we've got to do is try to do these projections of these things onto both axes. So if I've got my little diagram here and we're working out the tangent, then we're looking at the height here of, if I choose this point to be P, that's going to be, the height is going to be OP, and we've got here projection onto the x-axis, this on the y-axis, and here we've got the, if you like, the height or width of OP projected onto the x-axis. Now at certain points here, the projections of these things are going to become very large, and we're going to reach something we're going to call an asymptote as we try and do this. So we're going to try to draw out this graph here, and basically as this angle increases here, this projection is going to become closer to 1 divided by one number divided by the other one, and so what we're going to end up with here is a graph that's going to look like this one. Lost the protractor. So if we're looking for something like the tan of this, then we know at this point it's going to approach 1, and we know that the tan of 45 is going to be literally 1 over 1, which is going to give me 1. So the tan graph is going to give me something that is going to look basically like this. Now my problem is we're already hitting 1 at this point here, and this graph is now going to continue way up there, and that makes this really impractical trying to draw this one, because it's not going to work with these particular values. And so this graph doesn't quite fit in with this one, because when all my students try this, they try it exactly the same and it won't work, because we're looking at rather large numbers here to make it fit. So what I'm going to do is change the numbers on this axis, because it's the only way we can actually do this. And I can set my value of 1 perhaps much lower. So here we're going to have my value of 1 and minus 1. So now I can get this point on there, but as we go up, this is going to approach an asymptote, and it's going to come in on an asymptote at the 90, going across and 0 and coming down. And that gives us an approximation of our tan curve. Tan curve very much harder for me to try and draw, but it does cause some fun. So hopefully that's given you an idea about how these things work. We've got these different trig ratios. I do have a nice little machine that tries to draw the sine curve, made of Lego, and what we can do with this one is that as you get the circle moving, so it makes a sine curve, and it looks something. I'll put the link in the description of the model, but basically if we set up my protractor, and as I move this, what we can do is we can perhaps take a ruler here, and as I move this up, so you can see the line moves up, and as we get to the other side and come down, so this line moves down again. So if I then basically make a circle, draw circular motion, as I draw a circular motion here, my ruler, if I start at this point, is up as much as it can, and it's going to move down to halfway, and then it's going to move all the way down to here, and then as I move back that way, it's going to move back up to halfway, and then right to the top. So we're getting an up and down movement. If at the same time we move this one along, then what we find, we get, if we start up here, a cosine curve, and if we start at this point, then we would get, doing the same thing, so we'd start over here going up, we'll get a sine curve. So we can convert circular motion into either the sine or the cosine. As for whether we can try and do that with the tan, I've never tried, and it seems quite difficult. If I can, I'll try and put a link in the description so you can see a machine doing this to actually make it work. Anyway, that's it for this one, having a look at these sines and cosines and tans. I hope that explains it a little bit better, and it's worth trying to draw some of those things out. Anyway, until next time, if you like this one, subscribe, and I'll see you next time. Thanks for watching. Bye bye.